everyone. My name is Pitas Konstantinos, and I've recently completed my PhD at the LTS2 laboratory, headed by Professor Pierre Vandergeest at the EPFL, Lausanne, Switzerland. And today I'm going to talk to you about my recent work titled Dissecting Non-Vacuous Generalization Bounds based on the mean field approximation, which was published at ICML 2020. So just let me know if you have any questions during the presentation. And I'd also like to thank Omar and Maria for inviting me to give this talk. Now, we have this fundamental problem where deep neural networks have significantly more parameters than training data. So, for example, the VGG16 architecture has 140 million parameters, while the CIFAR10 dataset has only 60,000 training samples. Now, why is this a problem? So, we know from the bias variance trade-off that such a classification architecture should overfit. So it should have high training accuracy, but low testing accuracy. But this is not typically the case for deep neural networks. And in this presentation, we'll explore why do deep neural networks generalize well, and can we prove that they will generalize? Now, we introduce the following definitions. We have the learning sample X and Y, with X being the training signals and Y being the training labels. And these are generated according to distribution D. We have also a predictor, F, that turns signals into predicted labels. And we also have a loss function that quantifies the mismatch between the predicted labels and the true labels. And typically here in this presentation, we'll use the 0-1 loss, which is 1 for incorrect predicted label and 0 otherwise. We have also the empirical error rate, which is the empirical mean of the loss of the classifier for all training samples. And we have also the true error rate, or the risk, which is the expectation of the loss of the classifier over the distribution V. We have also the generalization error, which is the difference between the two. And what we typically want to do is we want to bound the true error rate by a constant. So essentially what we want to do is we want to prove that the classifier will have good performance outside of the training set and on the full distribution. Now, this is typically done using a validation set, and one would typically train on a training set and then evaluate the empirical error on a separate validation set. For example, assume a validation set X and Y of size M and a classifier with 0 empirical error over the validation set. And we can prove something to the effect that with high probability, the true error rate will be bounded by something that drops linearly with the size of the validation set M. Specifically, if we have 1,000 validation samples, we can show that the true error rate will be bounded by something like 0.0029, which is negligible. So essentially, the classifier will have close to 0 true error rate over the full distribution probably. Now, while validation sets are widely used, they have a number of limitations. So for example, validation samples could have been used for training. Even when samples are numerous, validation samples could have been used for training so as to improve both the training and testing accuracy. Now, at the same time, samples are scarce in some settings, for example, in healthcare, and it might be difficult to have enough samples even so as to get the, our training algorithm to converge if we try to construct also a validation set. Now, more importantly, there's no explanation as to why deep neural networks generalize. So for example, what are any desirable properties that we might want to enforce on our deep neural network so that it generalizes better? Now, a possible solution to that is complexity-based generalization bounds, such as PAC-Bayes bounds. And PAC-Bayesian theorems are roughly of the following form. They deal with stochastic classifiers with the posterior and apparent distribution. And they bound the true error rate using a complexity term that is the scale divergence between the posterior and the apparent distribution, and the empirical error rate. And notice also here that we have the expected empirical error rate. And to see why this is the case, we note that before we defined the empirical error for a single classifier F. However, here we have a posterior over multiple classifiers, and so we need to take an expectation over this posterior distribution. Now, also typically there's an inverse relationship between these two terms. There's an inverse relationship between the expected empirical error and the KL complexity term. And this is more clearly seen if we model the posterior and the prior distribution as Gaussians. And we center the posterior distribution at the minimum of the loss landscape and the prior at 0. And they will have an identity covariance with the shared scaling factor lambda. Now, for this modeling choice, the expected empirical error will have this form here, and unfortunately it can't be simplified a lot. But the KL complexity term has a simple analytical formula, and we see that it drops linearly with the scaling factor lambda. Now, for this reason, we can separate essentially between two cases. So we can separate between the case where lambda has a very small value, and in this case, the posterior distribution concentrates tightly around the minimum of the loss landscape. So here, the expected empirical error will be very small. At the same time, the KL divergence between the posterior and the prior distributions will be large, as these two distributions here are very different. Now, if we take the lambda scaling factor to tend to infinity, we'll have the opposite problem. So essentially here, the KL term, as we saw here, will tend to 0. However, the expected empirical error will be large, as we'll be averaging larger and larger regions of the loss landscape, where potentially the loss is not small. Now, this is the starting point of the paper that I'm presenting. And so most of the previous generalization bounds for deep neural networks were vacuous, meaning that they had values that were above 100%. They were bounding the true error rate with values above 100%. Now, we analyzed an existing non-vacuous bound based on PAC-Bayes due to Dagnan and others. And the main idea is to use an optimization procedure to balance these two terms that we mentioned before, the expected empirical error and the KL complexity term. Now, the problem when trying to optimize this objective here is that these two terms are non-differentiable. So essentially, here the KL term is non-differentiable in the general case, but also the expected empirical error has an expectation that's generally intractable for the highly nonlinear deep neural network. But also the loss here in PAC-Bayes bounds is typically the 0-1 loss, which is again non-differentiable.
Can I ask a question?
Sure.
Yeah, non-differentiable in what? Sorry.
Excuse me.
It's non-differentiable in what argument?
These terms. I mean, this usually it might not have an analytical expression right all of the times, and here we have this expectation that's generally intractable. It doesn't have an analytical formula, and then also here we have the 0-1 loss that well, it will only have well, it's piecewise constant. So then at least it's I think it's impossible, right, to take gradients there. At least you have to take a
okay. But
so I guess let me just
here?
I just wanted to jump in and clarify something. So in this, the empirical loss is still here with respect to the 0-1 loss. Is that the case, or is it with the cross entropy loss?
Yeah, so here, I mean, I'm just presenting a simplified form of PAC-Bayes bound, which usually is defined for bounded losses, right? So then typically here you frame it as with respect to the 0-1 loss. So the procedure that I'm describing here is one where, I mean, I'll describe later that I'll be substituting this 0-1 loss with the cross entropy loss, finding something, and then replugging it here in this expression.
Right. Because with respect to the 0-1 loss, then the non-differentiability is very clear, right? You have a piecewise constant loss surface, essentially. So I guess, yeah.
So
Okay, thanks.
this is dealt with different in different ways, right, in the literature. But I mean, actually, this is the next slide is about this.
Yeah, sorry to interrupt.
Yeah. And so here the way to solve this problem with these authors is to model the prior and posterior using Gaussians. So the posterior will be centered at the minimum of the loss landscape, and we'll have a diagonal covariance that needs to be optimized, and then the prior Q will be centered at the random initialization of the deep neural network, and we'll have an identical covariance with the scale factor lambda. Now here, these authors propose to optimize the surrogate using the categorical cross entropy and the reparametrization. So one would typically start from this objective here, that as we were discussing before is the full expression, let's say, of the bound. Actually, in the full paper, I'm using a different expression, but it's much too complicated to have here to this simplified formula. And so one would typically just substitute here the 0-1 loss with the categorical cross entropy loss, and then approximate the expectation using a number of Monte Carlo samples. And then one can also use the reparametrization trick to take gradients for the Gaussian distributions. And this is also related to variational inference from the Bayesian literature. So, so here one would typically, what one would do is, because lambda here would be assumed to be a free parameter, one chooses a value lambda, and then fine-tunes here this diagonal covariance so as to balance the two terms that we mentioned before. And now the results in this paper are non-vacuous. And we asked the question, which modeling choice contributes the most to non-vacuity? So for example, modeling the posterior covariance as diagonal is very restrictive in the types of posteriors that it can create. So how much optimizing it contributes to having a non-vacuous bound? So to answer this question, we do detailed experiments. And basically here, we have the original modeling choice for the posterior and the prior distributions, while highlighting the two important modeling choices, which is here the posterior covariance, which is diagonal, needs to be optimized using variational inference, and also that the prior is not centered at 0, but is centered at the random initialization of the deep neural network. And so we have these other three models here for the posterior and the prior, where we have none of these supposedly important modeling choices, and one at a time. So we make experiments using these models to see which one is important. And so crucially in these experiments, even though we could optimize also for the posterior mean, we instead keep it fixed to a minimum of the loss landscape, which we have found using manual stochastic gradient descent. And we do that because fine-tuning the posterior covariance and fine-tuning the posterior mean to balance the two terms and the objective that we mentioned before have very different intuitive interpretations. So for example, here, if we fine-tune the covariance, for example, by increasing lambda, one might hope to make these two distributions, the posterior and the prior, more similar, and therefore lower the KL complex term. Now, if one manages to do that while also keeping the empirical error small, intuitively this corresponds to having the posterior centered at the minimum of the landscape that is also lies in a flat basin. And to see why this is the case, if we have this lambda that's large, and we manage to both have the tail divergence being small, but also having the empirical error being also small, it means that as we're sampling further and further away from the mean, we need to be lying in a flat basin where the loss is small here. So in this way, this also represents a link to the deterministic classifiers with the solution in a flat basin. So potentially one can de-randomize the bound for the stochastic classifier and prove something for the deterministic one when it corresponds to a flat minimum. Now, by contrast, if we just optimize also for the posterior mean, we can potentially bring these two distributions closer and also reduce again the KL divergence between these two distributions. However, implicitly now we're measuring the flatness of a different minimum in the optimization landscape. So this connection with the deterministic classifiers is lost, and essentially we're finding a bound for a different classifier. Now, to compare the results, we introduce also of different models for the posterior and the prior. We also introduce risk complexity plots. So here on the x-axis, we plot the empirical risk, and on the y-axis, we plot the complexity. And so there are multiple benefits from these plots, and the main one is that we can plot here the region that corresponds to pairs of empirical risk and complexity, which correspond to non-vacuous bounds. So to see why this is the case, we note that the true rate for a 10-class classification problem, for example, for NIST-10, will be bounded by 90%, so by random choice, right? So then here, for example, if you have a classifier that has 20% empirical risk, we need to estimate the complexity that's at most 70%. So otherwise, we'll be making a trivial statement to the effect that the true rate is bounded by 90%. So of course, for a 10-class classification problem, it's bounded by 90%. Similarly here, if you have a 60% empirical risk, we need to estimate the complexity that's at most 30%, etc. So this is how we derive this line here. And this is how we shade this area here that corresponds to non-vacuous pairs. And we can also plot here, plotted using a star, the implied complexity when we measure the generalization error using a validation set. So for example, from this then, we know that, I'm presenting just a general example, and we know that from this then, there's lots of architectures that will have an empirical risk that's very small on the training set, but also they will generalize very well on the testing set, right? So then we're going to expect that the complexity of this classifier will be very small. And it's actually the target that we aspire using our bounding techniques. So any combination of empirical risk and complexity that we measure using our bounds, that is as close as possible to the origin, to the star, the better the bound would be. And another benefit of this plot is that we can also plot multiple estimates for a single model of posterior and prior distributions. And to see what this is useful, we saw before that we can actually we have this lambda scaling factor here that that trades off between the expected empirical error and the KL complexity term.
Can I jump in with a quick question?
Sure.
What determines the location of the dashed line? The dashed line is the plot of the bound itself, right?
So the line here is just that. So let's say that we have a 10-class classification problem, right? So if we have a classifier that has an empirical risk that's 20%, and we want to estimate this complexity term here, and essentially the sum of these two terms is our bound, right, on the true error rate. So the only thing that I'm plotting here is that this thing here needs to be less than 90% to be meaningful.
Right.
The sum so here so this line just corresponds to, so it's 20 plus 70 here. So this is anything above here, right? For 20%, yeah. If we estimate the complexity, that's 100%. This is a trivial statement. We'll just say that the true error rate is less than 120%.
Any way to see the effect of varying beta? Varying beta would move this dashed line, right?
So actually here, I'm having a simplified version here. So yeah. Actually, let's say I'm taking, actually lambda is a free parameter, but also beta here is a free parameter. And so here, roughly, you go from L tending to infinity, where, as I said before, the complexity, KL complexity term will tend to 0, and the empirical error rate will be large. And here, lambda, when lambda tends to 0, the empirical risk will be small, but the complexity will be large. as I described in the previous slides. But also here, basically one needs to, I mean, at least what I'm doing here is that I'm also taking a grid over beta, which is another free parameter. And so what that creates is actually some curves here, like this. And I'm just taking the value that's the combination that it's closest to the origin. So in a way, it's yeah, these two free parameters are related, but in any case, you can always take essentially a Pareto form that's closer to the origin. So anything that's that stores the origin from here will be better than this estimate.
I'm just wondering what the advantage of plotting it this way rather than just plotting the bound on the y-axis is.
Sorry, excuse me.
What's the advantage of like this term is what, like the bound, the minus the risk or something versus the risk? What's the advantage of plotting it this way rather than plotting just the bound value against the empirical risk?
The bound value. I mean, I think also probably you can also plot it in that way. Basically, up until now, the reason that I kind of like introduced this plot here is that usually one would just give single estimates, right? So they would just say my bound is 50% or something like that. So I find that this is less intuitive comparing single values. Let's say that you have two techniques for bounding the generalization error. I just find that it's a bit, it might be a bit misleading to compare single values because you might, let's say that you choose, since lambda here is a free parameter, you might have for one technique something that's here, so that it's suboptimal, and for another technique something that's here or here, so that then you are essentially you are comparing two things that are not really comparable. So just I think that it's better to just have the free parameters, take a grid over the free parameters, create a front as I have created here, and then we'll see that basically you have multiple estimates for different modeling choices, and I think that that's more intuitive compared to single estimates. But then
that makes sense. That wasn't really my question, but it doesn't really matter that much. I think I can see that like that is basically equivalent to plotting the bound against the risk.
Yeah, exactly. So it's just another choice. Of combining essentially kind of like a linear combination of these two, right? So it can be also I think what people propose. But I haven't seen someone comparing bounds in this way before. So.
Yeah, sure, thanks.
So here basically we have the results of our experiments. And we tested the aforementioned for combinations where we have this this model here with these two important modeling choices, one at a time, and none of them at this, none of them. And so here we test also 60 different data sets. So we have the NIS10 and the CFAR10, and also two other data sets for each hyperset, let's say, of each original data set. Where we collapse the 10 classes into 5 and 2 respectively. So this, maybe it's a bit easier, let's say, to solve for the neural network. And we test a single fully connected architecture. And so here, basically, you notice that these two models have the prior centered at 0. And we see that for NIST, we'll focus on this image here, and we'll see that we have, again, this multiple estimates for multiple scaling factor lambda, also beta, but I was kind of hiding it here for simplicity. So we see that when the prior is centered at 0, all the estimates are vacuous for NIST. Now, as soon as we change these two models here, where the prior is centered at the random installation, we have a big improvement in our bounds, so they become non-vacuous. They tighten significantly, they come much closer to these to the origin here. So yeah, we have a big improvement. And now one will notice that here this these green samples here correspond to having not only having the prior centered at the random initialization, but also having a diagonal posterior covariance that is optimized with mean-field variational inference. And basically, we see here that starting from the prior centered at 0, we move here to the prior centered at the random initialization, and we have improvements. But then for the green points here, where we further optimize the posterior diagonal covariance, we don't really get any improvement. And so this is the same across all mixed datasets. And interestingly, for the CFAR datasets, all the model combinations are vacuous. All the bounds are vacuous. We cannot get to the region of non-vacuous. Now, why does mean-field variational inference result in few gains? So it might be restricted modeling or problems with variational inference with optimization procedure. And we know that variational inference is known to have problems converging to good solution due to gradient variance. It might simply be that we need better optimization procedures with lower gradient variance. So to test, to try to see what's the problem here, we optimize the posterior and the prior covariance in closed form. And we relax slightly the modeling on the prior so that its covariance is diagonal. And we present these two theorems where in one we optimize the posterior covariance in closed form, and in the other one, in the diagonal case, we optimize jointly the posterior and prior covariance in closed form. Now, one will notice that actually optimizing the prior covariance doesn't result in a valid prior, as PAC-Bayesian prior should be independent of the training set. However, it does serve as a sanity check to what is possible using the diagonal modeling. And now here we note that theoretical analysis is in general difficult with this objective because the categorical cross-entropy loss landscape is highly non-convex. Now, however, we notice that we're actually interested in a posterior that's very specific. So it's a Gaussian with a fixed mean. And so since it's a relatively small variance, so then the posterior will concentrate around the local region of the loss landscape around the minimum where we have centered the posterior distribution. So then if we kind of assume that here locally the loss function is quadratic, we can approximate this term here using a quadratic. And this makes our calculations easier. And I've just, in the paper, I also have some experiments where I'm arguing that empirically it does seem to be the case that locally the loss function is quadratic. This has also been replicated in a number of other experiments, in other words. And so here, basically, what I'm doing is that I'm going to the NIST2 and CFAR2 datasets. I'm at the minimum of the loss landscape that I found using stochastic gradient descent for the deep neural network. And I'm taking some random directions along this loss landscape. And I'm just plotting here the projections along these random directions. And so here, one can see that for these four, but also for other ones, the loss is locally quadratic, at least empirically. And so here, these shaded areas here also correspond to where we kind of estimate that the samples from this posterior distribution concentrate somewhere here in these strips. So we see that also not only is around the minimum is the loss locally quadratic, but also our posterior sufficiently concentrates around the mean, so as for this approximation to the mean. And so what's the result of this, of optimizing closed form? So basically here, we have the results from optimizing in closed form the posterior covariance and the prior and posterior covariance jointly. So again, focusing here on this image for the NIST5 dataset, we see that when we optimize the posterior in closed form, as opposed to using mean-field variational inference, there is some improvement, but there is some improvement. And for optimizing the prior and posterior, there is also a bit of improvement. But actually, they're not, we can't really say that it's that significant. And this is the same for NIST and for NIST2. And also, interestingly, for CFAR, we can't really get away from this vacuous estimates. So basically, even if we, and this is also cheating, right? Prior and posterior optimized jointly, but we can get to something that's non-vacuous.
Quick question here. The top 3 plots, what made the dashed line be curved rather than straight here?
Because it's the scale here is this logarithmic. Yes, I've changed the wait. No, it's
Okay, got it. Yeah, I see the horizontal scale is logarithmic. I missed that.
Yeah, because here basically these results are kind of very close here to the origin, so then I'm just change the scales. That's one. And so basically here the main problem seems to be the diagonal modeling. And since now we're not really optimizing using variational inference. And the main problem seems to be the diagonal modeling and not the optimization procedure. Now, for the previous reasons, we look at more expressive posteriors, and modeling more expressive posteriors is a topic of intense research in binomial network literature. However, existing solutions are too slow, both in finding the optimum of the parametric family of distributions and or when sampling from the derived posterior. So as such, we work with block diagonal Gaussian posteriors that can be optimized in closed form and from which one can efficiently sample. And we only consider correlations between weights of each neuron, so very small blocks. So essentially, we are moving away from these Gaussians that have a diagonal covariance to some that's block diagonal, but the blocks that we have are very small. But still, we do get significant gains. So here, these are all experiments for NIST. And one, we should remember that here, the bound values here are for optimizing the prior and posterior jointly in closed form. So essentially, here we're cheating. But even though we're cheating here in our baseline, we do get some gains here from having a more expressive posterior. So this is maybe something like 5 to 10% of an improvement in our bound tightness. Now, the above results can be linked to better modeling the curvature of the loss landscape around the minimum. And I'm just going to mention here briefly that the way that we approximate the Hessian is related to KFAC. It's basically a simplified version of KFAC. So basically here, let's say that we have this neural network here, and we have this input signals. So then these are, we can stack them into a matrix that has the dimensions and has consists of n signals. And basically we construct these local Hessians here, where this consists of the inner product between of the A and the A transpose. And I'm just going to mention here that this is related to the Fisher matrix, and which can be seen as an approximation of the Hessian. Now, the key takeaways are that regarding flatness, flat minima are important for generalization, but using the mean field approximation is too restrictive. And we need more expressive models of curvature around minima, so block diagonal, KFAC, etc. Now, also regarding priors, we saw that choosing the prior mean to be the random neural network initialization was important. So maybe can we learn even better priors through data? And this is something that I have been working on a little bit, and we'll do soon about that. So thank you for your attention. That was all for me. And yes, I'm open to questions.